till now we have implemented muxes, right? 2 cross 1 mux, 4 cross 1 mux and 16 cross 1 mux, like that. Now we'll implement muxes using MUX tree concept. I'll tell you what it is. This is one important concept, that is, there is a one question like implement four cross 1 mux using 2 cross 1 mux. You may get a question like this, that is 4 cross 1 mux implementation using 2 cross 1 mux. During these cases, we'll use the concept of MUX tree. Right? Here the required inputs are what? Required input lines are 4. Right? But available inputs only 2, right? So I will consider 2 cross 1 mux, right? So with this 2 cross 1 mux, I will get only 2 inputs. I am getting only 2 inputs, right? So but we require 4. For that, I will consider one more 2 cross 1 mux. Now you just see, here we are having a possibility of 2 inputs. Here also we will have a possibility of 2 more inputs. Totally 4 inputs are possible. Fine. So first we will require 2 muxes, right? Input wise is okay, but you just check the output. If I consider like this, I am getting 2 output values, right? One output for this mux and one more output for this mux. So during these cases, I will use one more 2 cross 1 mux. Now I am having only a one output. Right? At the input side, I am having 4 inputs, and at the output, I am getting only one output. So this is called MUX tree. By using this MUX tree concept, we can implement this 4 cross 1 mux using 2 cross 1 mux. You just see here the number of 2 cross 1 muxes required are 3. At the input, we require 2 muxes. At the medium level, we require one more mux to get the 4 cross 1 mux values. Okay. But every time considering this mux tree is difficult. So instead of that, this we can write in a formula based, that is, just assume the required inputs are n. Divide this required inputs with available inputs, then you will get 2. We need to do this division till this value becomes equal to 1. So this is like a successive division. So initially divide required value by available, then you will get 2. Then again this divide this 2 value with the available inputs, then you will get 1. Right? So initially we require 2 cross 1 mux. At the end we will require again 1 2 cross 1 mux. The total number is 3 2 cross 1 muxes are required. Okay, means here whatever the quotient value we are getting, that is nothing but number of 2 cross 1 muxes required. Okay, fine. So in this way we can implement higher order muxes like this using lower order muxes. So now we came to know how many muxes are required, which are 3. Now I will implement this values. So as we require 3 muxes at the first level, we require 2 muxes, right? Then the next level we require 1 mux, 1 2 cross 1 mux, right? I am considering only the muxes number. Now I will develop the truth table for 4 cross 1 mux. As we know, for 4 cross 1 mux, we will have 2 selection lines are required, which are S0 and S1. Truth table. I am assuming enable is high. So for 0 0, I0 will be selected. For 0 1, I1 is selected. 1 0, I2 will be selected. For 1 1, I3 will be selected. For all these cases, enable is high, like this. So this 4 cross 1 mux truth table we need to implement by using this 2 cross 1 muxes here. Okay. So as we are having 4 inputs, I will consider 2 inputs here. Let's take I0, I1. The remaining are I2 and I3. And output is Y. So there is a connection, these two are connected to this, like this. Now, where we need to choose these selection lines, right? Where we choose S0 selection line and S1 selection line. As we are having only 2 selection lines, but we are having 3 muxes, right? Here you have to remember one point, that is, for each stage, this is one stage, first stage, this is second stage. For each stage, the selection line is fixed. For example, if I am considering S0 for the first stage, means here will require only S0 and here also require S0. For this stage, obviously S1, like that. Instead of that, if I consider S1 here, then entire first stage selection line will be S1 itself and the second stage selection line will be S0. Okay. So for each stage, the selection line value is fixed. So as it is 2 cross 1 muxes, we will have only one selection line is required. For a while, I will assume that first case selection line value will be S0 and the second line selection value will be S1. Now we will check for this representation whether we are getting I0 value or not. For the first case, you just see S0 0 and S1 0. So S0 is 0, S0 0, S1 0. Then actual required output is I0, right? We will verify here also whether we are getting I0 value from this circuit. See, when S0 is 0, as we have discussed, the first input will be transferred to the output. So here you will get I0. Okay. Here also S0 is 0 means what? First data will be transferred to the output. First data means I2. Right? So first I know the outputs for the first stage, but I didn't get the final output value, right? So I will verify here itself. Here also I am having 2 inputs, I0 and I2, right? So when S1 is 0, it will select, means this mux is select only the first input. So what is the first input here? I naught itself, right? So from this, our assumption means this stage is having S0 selection line and this stage is having S1 as a selection line is correct. We'll verify the one more case also. Let's take, if I assume this one, 1 0, okay? 1 0 means S0 value is 0 like this and S1 is 1 itself, right? During this case, the required output is I2. Actually, the required output is I2. So, from this combination also, we will verify whether we are getting I2 value or not. Okay. So, here 0, 1. First, we will see the output value for this stage. S0 means first value will be transferred. So, so here I0. S0 first will be I0, fine, I2. See, when S1 is 1, obviously the second data will be transferred as the output. The second means what here it is? I2 is transferred as a output. Correct. In this way, we can verify all the values. If you are assuming, we'll verify one more also. For 1 1 also, we'll verify whether our design circuit is working properly or not. That is a verification here. Okay. Actually, for 1 1 combination, we need to get I3 as output. Right. So, 1 1 combination, here S0 value is 1, here also S0 value is 1. Here S1 is equal to 1. That is our last combination, right? Now you just see. When S0 is 1, what will happen? 0 means first data will be transferred. 1 means second data. So, as it is 1, I1 data will be transferred. So, here output is I1. Similarly, S0 is 1 means second data. I3 will be transferred here. Now, for this 2 cross 1 MUX, again the selection line value is 1. When it is 1 means the second data is what? I3 will be transferred as the output. So, from this our designed circuit is correct, right? So, in this way we can implement 4 cross 1 MUX using 2 cross 1 MUX. Here the important thing is how we are choosing these selection lines. That is very important, and there is a one thumb rule that you always starts from the LSB bit itself, means for the first stage consider S0, next stage S1, for the next stage if you have S2 take S2, like that. That is a one thumb rule to design this higher order MUXs using lower order MUX. I will solve one more numerical so that we will have a better understanding on this concept. We will implement eight cross 1 MUX using 2 cross 1 MUX. Okay. For this implementation, first we need to find how many 2 cross 1 MUXs are required. For that, find required inputs. Let's take n is 8, but available is what? Available inputs are 2. This is required input and this is available input. To get the total number of MUXs, divide required by available. Then you will get 4. We need to do this process till this quotient part equal to 1. So as we are having 4, again divide 4 by 2. Then we'll have 2 and 2 by 2. Then you will get 1. So here we can stop because here we are getting 1 value. 1 is nothing but this is final output. Here this is given input. 8 and ultimately you are getting 1, right? Okay, with this we can stop here. Now, the total 2 cross 1 muxes required are 4 plus 2 plus 1 means 7 2 cross 1 muxes are required. Okay, that is the one thing. This is counter, total. 4 means, for the first case we are getting 4, right? So at the first stage, we require 4 2 cross 1 muxes. 2 means at the second stage, we require 2 2 cross 1 muxes. This is third stage, we require 1 2 cross 1 muxes. Out of 7 muxes, these muxes are classified into 3 stages. First stage 4 and second stage 2 and third stage is 1. So now I will consider with this. And third stage we require 1 2 cross 1 mux. Okay. So for each 2 means 2 inputs, 1 output and 1 selection line. For 2 cross 1 mux we know only 1 selection line. Again for this 2 inputs, 1 output, 1 selection line. For this 2 input, 1 output, 1 selection line. 2 inputs, 1 output, 1 selection line. For this also 2 input, 1 output, 1 selection lines. 2 input, 1 output, 1 selection line. Again for the third stage 2 input, 1 output, 1 selection line. This is a general structure, right? Now we need to implement 8 cross 1 function by using this combination. For 8 cross 1 mux, we know the truth table that is zero 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 I0 0 0 is 1 I1 0 1 0 I2 0 1 1 I3 1 0 0 I4 1 0 1 I5 will be transferred 1 1 0 I6 for 1 1 1 I7 data will be transferred, and I am assuming for all this combination enable value is high itself. Okay, right. So as we are having 8 input lines, I will consider 8 input lines here. Let take inputs are I0, I1, I2, I3, I4, I5, I6 and I7. Output of first stage is connected to the second stage. And output of second stage I am connected to the third stage. Right. And ultimately we require a final output Y. Now the thing is, what is this selection line values? Right. As I already told to you, for each stage the selection line will be fixed. Means if you choose here S0, S0 means S0 value is fixed for all the first stage muxes. Similarly, if I fix S1 here, S1 is fixed for all the second stage. S2 is fixed for all third stage, like that. As I already told you, we will always start from LSB for the first stage. So I am assuming S0 here and S1 for the next stage and S2 here. So now I have implemented 8 cross 1 mux using 2 cross 1 mux. Now the thing is, we need to find these output values, means whether for this connection, whether we are getting this output values or not. For that, randomly I will choose 3 combinations. Let's take these 3. For the first combination, what it is, 0, 1, 0. For this combination, you need to get I2 value as the output. The same thing we will verify here. S0 is 0 and S1 is 1 and S2 is 0. So for this combination, we will check what we will get with this logic diagram. Okay. Just see, when S0 is 0, S0 0 means first data will be transferred as output. So for this mux, first data is what? I0. 0, first data, I2. S0 0, first data, I4. S0 0, for this first data is I6. Fine. First stage output is known one. Now coming to the second stage, 1 means second output, the second input will be transferred as output. So when S1 is 1, obviously I2 will be transferred as output. So S1 is 1, second means I6 will be transferred. So here you will get, now I know the second stage data also. Now for the third stage, just see here, the selection line value is 0. As selection line is 0, then first will be transferred, means ultimately you will get I2 value. Actually, you need to get I2 value for this combination. Here also we are getting same result as I2, right? We will verify with this combination also. Let us take 1 0 0 combination. 1 0 0 combination means S0 is 0, so instead of that we will take this combination. 1 0 1 combination. For S0 combination, just see, S0 value is 1. Okay, for this combination, S1 is 0 and S2 is 1. We will check what we will get as output. Okay, when S0 is 1, means the second input will be transferred as a output. Second input, here it is I1, here it is I3, I5 here. Second input is what? I7. Fine. Here the selection line value is 0. 0 means what? First data will be transferred. First means I1, here the first is I5, right? Now S2 is 1, means second data, second line input, second input line will be transferred as output. So second, 1 means second is what? I5. So again you are getting the same value as output. So in this way, we can implement higher order muxes like 8 cross 1 mux using a lower order mux, that is 2 cross 1 mux. Okay. Now we will implement 8 cross 1 mux using 4 cross 1 mux. This is actually a special case. We will see why it is special. First thing is what? Ultimately, we need to find how many 4 cross 1 muxes are required to implement 8 cross 1 mux, right? Here the required is what? Required inputs are 8, but available inputs only 4. 4 cross 1 mix, 4 cross 1 mux, so 4 available inputs. So during this case, we need to divide required by available, then you will get 2. we need to divide this till this quotient value is equal to 1. So, as it is 2, again divide 2 by the available 4, it is 0.5, right. 2 means 2 4 cross 1 muxes are required. At first stage. That is the meaning of 2. Then what is the 0.5? We don't have any half like size of muxes. So, during this case, we will use enable to implement this. First, we will use only 2 4 cross 1 muxes for the first stage, and second stage we will see what we need to do. For the first stage, 2 4 cross 1 muxes is required. So, I am taking 2 4 cross 1 mux. As we know, for the 4 cross 1 mux, 4 inputs are there. Let us take, and 1 is output, and 2 selection lines are there. This is a common structure. Similarly, for this 2 cross 1 mux, again 4 inputs are possible. 1 means single output. 4 we can write as 2 square. So, 2 selection lines are required. Fine. Okay. So, before implementing this circuit, first I will consider 8 cross 1 mux truth table. For 0 0 combination, output is I0, I1, 0 1 0 it is I2, 0 1 1 I3, 0 1 for 1 0 0 I4, 1 0 1 I5, 1 1 0 I6, 1 1 1 I7. Okay. The previous cases we are directly assuming E as 1, right. So, as we are having 8 inputs, I1, I2, I3, I4, I5, I6 and I7. For the second stage, we require half mux. As we don't have any half mux, right. So, instead of using a mux, the same functionality like mux will have one more logic gate, that is nothing but OR. So, I am considering OR gate here. So, we will expect output as Y, right. Fine. So, as we are having 3 selection lines here, but the required selection lines are only 2. So, I am considering S0 and S1 here itself. Then what we will do with S2, right. Here only 2 selection lines are required. So, the third selection line will assume as a enable here. Means that selection line will consider as a enable itself. So, I am taking enable. This enable is what? S2 itself. This enable is S2 itself. But if you observe, for the first 4 cases, S2 value 0 means what? Your enable is also 0. So, when enable is 0, irrespective of your selection lines, and your output will always becomes equal to 0, right. To avoid that, here we will use one NOT gate. To use this combinations also, I am using one NOT gate here. Now, you just see what happens here. For the first combination, Let's take this is the combination where S2 is 0, okay, and S1 value is 0, S0 value is 0. During that case, this is enable. During that case, what will happen? As S2 is 0, for the second mux, enable value is 0. We know the enable concept, right? When enable is 0, irrespective of this selection line values, your output is directly 0. No need to evaluate this 4 cross 1 mux values. As enable 0, output is 0, right? At the same instant, when S2 is 0, as we are NOT gate using here, enable value becomes high, right? Enable is 1, these two are 0. Enable 1 means this mux is in on condition, right? Now, for 0, 0 selection line, we know I0 will be transferred here, right? Now, what is the function for this OR gate? OR gate is the sum of all the inputs, means I0 or 0. Then you will get I0 itself. So, you are getting I0 value directly with this circuit also, right? For the next case, I will choose one more combination. So, during these 4 cases, means during this 0 combination, what will happen? During this period, this 4 cross 1 mux is always in off position itself. Only this mux is in on condition. That is the one thing. So, no issue, the output, the data will be transferred through like this. Now, if I consider this period what will happen? S2 is 1, right? When S2 is 1, for the second mux enable is 1, but for the first mux enable value is 0, right? Because S2 is given to 1 NOT gate, 1 complement becomes 0. So, during this period, first mux off condition, because as enable is 0, irrespective of your selection lines, output is always 0. So, during this period, only second mux is in operation. So, we will take 1 0 0, S2 is 1, these two are 0 0, means what will happen? 0 0 means first data will be transferred. So, I4 is transferred. Output is what? Y is equal to I4 plus 0. So, ultimately output is I4, like that. So, here the thing is, so during these cases, means when we are getting half mux concept, then we will use MSB as an enable. MSB as an enable point, and at the end we will use OR gate to implement this 8 cross 1 mux using 4 cross 1 mux. Thank you.